Hello. In the last class we have reviewed some exercises. I mean, while solving exercises we have reviewed some of the single step methods. So, let us continue to do that, and we missed maybe solving system of equations, and then of course, we have learned RK methods, but only explicit. So, maybe with reference to some implicit nature. So, let us try to attempt some problems. Okay. Yeah. So, this is tutorial 2, still continuing single step methods. Okay. Solve for y of 0.3, 0.6 when y x is the solution of second order equation so we need two initial conditions. Sorry. Okay. Choose h is 0.3. Okay. So, solve for y of 0.3 and y of 0.6 when y x is the solution of the second order equation, this initial value problem, and choose h 0.3. So, that means to compute y of 0.3 with this, so x 0 is 0. So, y of 0.3 is y 1, y of 0.6 is y 2. Okay. So, now as we discussed earlier, so this is a second order. Okay. So, what do we have to do? Convert it to coupled system of first order equations and then try to adopt one of the methods. Okay. The story is not over. Okay. Which method we have to mention? Okay. So, solve using Rangakutta of order 4. Okay. Right. So, if we solve Rangakutta order 4, then a lot of general idea we may get. Okay. So, what was our equation? Y double minus x y dashed plus y equals 0 and y of 0 is 1 and y dash of 0 is minus 1. Okay. Right. Okay. So, now we have to convert this to system. Let y dash is z. So, then this becomes, this implies z dashed minus x z plus y equals to 0. So, therefore, we have the following system: y dash equal to z, z dash is minus y plus x z, y of 0 is 1 and y dash of 0 becomes z of 0 is minus 1. Okay. So, this is our system. Okay. So, this is our system that we have to solve. So, now since, so remark, x is independent variable, y and z dependent variables. So, therefore, when we use RK fourth order, we have to be careful and we have to define two different functions. Okay. So, how do we define? So, the general with reference to general system, y dash equals to f of x y z, which is z, and z dash is z of x y z, which is minus y plus x z. Okay. So, corresponding to y, we define specific functions, and corresponding to z, we define different functions. Okay. So, how do we do? So, how do we do? Y n plus 1 equals y n plus h by 6 k 1 plus 2 k 2 plus k 3 plus k 4. Okay. Right. Then, so we define, so let us have simultaneously z n plus 1 z n plus h by 6. So, we have to use a different notation. Okay. So, let us use a different notation, L 1 plus 2, L 2 plus L 3, L 4. Okay. So, what is K 1? K 1 is f of x y z, and what is L 1? G of x y z. Okay. Then K 2 okay. Therefore, L 2 okay, and K 3 L 3 K 4 L 4 okay. So, these are the two different coupled. So, unless you compute K 1, one cannot compute L 2. Okay. So, unless we compute L 1, one cannot compute K 2. Okay. So, they are coupled, right. So, let us proceed further. So, now n is 0. So, we have f of x y z is f of x y z is z, g of x y z is minus y plus x z. Okay. So, k 1 is so let us write down the given data as well. Y 0 is 0, z 0 is minus 1, x 0 is 0. So, z 0 is minus 1. And what is L 1? So, this is 0, 0. So, L 1 is y 0, sorry, y 0 is 1. So, this will be 1 minus 1. Okay. So, this is minus 1. Then k 2 is z 0 plus h L 1 by 2 minus 1 plus L 1 is minus 1. So, this will be this L 2 will be minus. So, this on we have defined L 2 is, so we have all three involved. So, the increments are h by 2, h k 1 by 2, h L 1 by 2. So, from here minus y 0 plus this plus x 0 plus h by 2 z 0 plus h L 1 by 2. So, this will be minus k 1 is minus 1 plus x 0 is 0, z 0 is minus 1, L 1 is minus 1. Okay. So, this will be minus 1 minus okay. So, this will be so, this is our L 2. Now, K 3. So, L 2 okay. So, this will be then L 3 K2 L2 okay. So, this will be then K4 L3. So, this is then L4 K3 value is minus Y0. So, this is Z0. So, this is Z0. So, this can be simplified and we get minus point. Okay. So, having obtained these values, we have y of y0 h by 6, okay. Then k1 plus 2 k2 plus 2 k3 plus k4. So, this L1 plus 2 L2 plus 2 so this can be okay. So, y of 0.6 left as an exercise. Okay. So, similar method. So, you can try to do it. Okay. So, with the RK method we could solve system. So, that we get both simultaneously, that is how to use RK method and simultaneously how to solve system of equations. And if you observe the RK method which we have discussed, both second order and then 3 stage and fourth order etc. So, these are all explicit. Okay. In fact, Taylor series is explicit method and all that. So, there are some methods which are implicit. So, what do you mean by implicit? So, we will discuss in detail when we go to multi-step methods, but just a brief what is implicit method, and then we quickly look into implicit Runge-Kutta method. Okay. So, let us do that. So, suppose a method is defined as y n plus 1 equals to y n minus 2 plus 3 f n plus 1, and this f n plus 1 is f of. So, that means we are asking for computing y n plus 1, but right hand side is also asking. So, such method is implicit. Okay. Right. So, let us look at it is a kind of problem only, but in terms of implicit RK method. Derive an implicit Runge-Kutta method of the form So, you may observe why we are calling this implicit. So, you have left hand side you have k 1, but right hand side as well you have. Okay. So, derive an implicit Runge-Kutta method of the form this that is second order. Okay. So, how do we proceed? So, we in general in explicit we have learnt, we have expanded this in Taylor series, and then we have expanded this in powers of h, and then we expanded the y of x n plus 1 in Taylor series, and then match the coefficients of equal powers of h. Similar sort of thing we need to do here, but you may observe right hand side you have k 1 and left hand side we have k 1. So, that means, if you keep on substituting k 1 this same expression, recursively k 1 will be sitting on the right hand side. Okay. So, let us see how do we proceed further. So, k 1 I am expanding. Okay. Alpha h dou f by dou x plus beta k 1 okay. So, the higher order terms etc. So, this is h f n alpha h square plus h beta dou f by dou y k 1. Okay. So, k 1 is sitting. So, now again we need to substitute k 1. and the other terms. Okay. So, therefore, y n plus 1 is y n plus w 1 h f n plus, if you multiply this, h square beta h square beta f n dou f by dou y plus h cube terms. Okay. So, plus okay. So, Taylor series so, now comparing these two, okay, because the method is second order, we compare up to h square. So, this approximates this, and for f w 1 must be 1, then for f x coefficient is half there, and here alpha w 1 is half, then for here w 1 is half. Okay. So, this implies alpha equals to beta equals to half. Okay. So, therefore, y n plus 1 is y n plus h x n plus h by 2 y n plus k 1 by 2, where k 1 is so it is recursive. Okay, because if you substitute, we keep on getting k 1 recursively, k 1 there, k 1 again, if you substitute again you get k 1, but nevertheless up to second order, by comparing we get the coefficients, and then this is an explicit. Why it is explicit? You can recall k 1 we are expecting to compute, but it is given on the right hand side. Okay. So, this is a very important observation in implicit RK method. Okay. So, let us solve some problems. Okay. But one remark before we proceed is, generally expanding in a Taylor series is very difficult. Okay. Because recursively how long we do it. So, it is so let us see through this example slightly different story. With h equals to 0.3 using second order implicit method. Okay. Right. So, just now we have derived by expansion. So, now we would like to solve a problem. Okay. So, this was our implicit RK method. Okay. For the given problem, f of x y is this, x 0 is 0, y 0 is 1. Okay. Right. Now, let us try to compute k 1 h f of this. So, therefore, minus 2 x n plus h by 2 y n plus square. Okay. So, minus h 2 x n plus h which is an implicit equation for k 1. Okay. And one may use any iterative method, because we have to solve for k 1. See, this we have to solve the problem. If you keep on substituting recursively, so there is no end. Okay. The method has been obtained in that fashion, but now we would like to compute the solution. So, this is an implicit equation. So, we have to solve using any iterative method. So, to this extent, let us define f of k 1 as k 1 plus h okay. So, this is k 1 h is 0.3 . Okay. So, now since it is any iterative method, we try to use Newton-Raphson method. Okay. We propose to use Newton-Raphson method. So, therefore, k 1 s plus 1, so L plus 1 minus okay. So, let us propose to have Newton-Raphson method. Okay. So, accordingly, let us compute. So, now we need an initial guess. Assume k 1 0 equals to h okay. So, this is f, our f was minus 2 x 0 square y 0 square. So, this is minus 2.3 x 0 square 0. So, k 1 is 0. Okay. So, now let us compute f dashed. So, f dashed of k 1 is 1 plus 2 times half. So, this is 1 plus 0.3 2x and 2 to get cancelled, n plus this. Okay. Now, so this will be x 0 y 0, so 1 plus k 1 0 0 . So, this is equals, okay. Then f of k 1 0, this will be so this will be okay. So, therefore, so we have f of this is f dashed of is, so therefore, k 1 1 is so this is minus, so this is k 1 prime. Now, we have to compute f of k 1, sorry, not k 1 prime, k 1 1. So, now we have to compute this. Okay. So, you may do using calculator, and also we need this, and hence k 1 2 we get okay. So, one may stop here or proceed until so we proceed until two consecutive, the difference of the two consecutive values is less than epsilon, some pre-assigned, we proceed. So, let us say here we stop. So, when we stop, we get, so this is y 1, so y 0 plus K1. So, this is the answer. Okay. So, this is how to solve using implicit RK method. Okay. So, now we have solved a lot of stability problems for the explicit. So, let us do it for implicit. Okay. Find the region of stability for the implicit Runge-Kutta method given by this for the IVP. Please make a note. So, this is a case of f of x y equals. Okay. So, there is no explicit dependency on x. Okay. So, this is a kind of a special case. Okay. So, now for this we would like to have stability interval. Okay. Stability analysis. So, now let us proceed with our reference equation y dashed equals to lambda y. This implies K1 is h and K2 is h So, you can see K2 is implicit. So, K1 lambda h y n. Okay. So, okay. So, since K2 is explicit, we try to collect the coefficients and solve as an algebraic equation. Okay. So, this implies so this is kind of algebraic equation. Let so then we have Okay. K2 equals so this is our K2. So therefore yn plus 1 is yn plus, so what was our method? Yn plus 1 by 4 k1 plus, so this is yn plus 1 by 4 okay. So this is our difference equation. Okay, is the difference equation whose characteristic equation is okay. So this is the characteristic equation. Okay. So now once we have the characteristic equation, so the procedure is for absolute stability we have to put the condition of on the roots and then try to determine. Okay. So let us do that. Okay. For absolute stability, okay, where lambda is negative, so this implies -1 okay. So this implies okay, right. So from this we get look at it. So if you bring it this side, so we get h bar, so h bar by 6, okay. H bar 6 plus h bar is less than or equals to 0, okay. And since lambda h is 0, or h bar is greater than or equals to minus 6. So, this is one side. Okay. So, then we have to see for the left. So, this is the right inequality. Now, we have to see the left. Okay. So, the left inequality okay. So, this gives so minus 2. Okay. So, this gives and which is true for. So, this holds and this is true for h bar greater than or equal to minus 6. So, therefore, the stability interval. Okay. From the left from the right we got h bar greater than or equal to 6 and from the left inequality this and this holds for this. So, the stability interval minus 6 to 0. Okay. So, for implicit the problem with the implicit is for deriving the method we have used a Taylor series, but then for a specific method we have to solve an algebraic equation. Okay. Sometimes it is nonlinear and that we have solved using Newton-Raphson method. Okay. So, now let us have some exercises for your for benefit of practice. Okay. Okay. Obtain solution of the system y dash equals to z dash equals to minus 4 y minus 2 z, y of 0 is 1, z of 0 is 1 by Euler method to Rangakutta fourth order. Okay. Using step size h equals to 0.2. Okay. Obtain the solution of the system using step size h equals to 0.2. Compute y of 0.2, y of 0.4. Okay. Right. 2. Use implicit Rangakutta method of second order to solve y dashed equals to x plus y, y of 0.4 is this with step size h equals to 0.2. Okay. Compute y of 0.6. Okay. So, these are some exercises for you. You can try and then feel more confident on both explicit and implicit RK methods. However, as I mentioned, we discuss in detail what is an explicit method, okay, when we proceed to multi-step methods. Okay. So, let us wait for the lectures on multi-step methods to hear more on implicit methods. Okay. Thank you. Until then, bye.